Alright, hell yeah. So we have statics. And check it out. I was at a coffee shop, and so I'm just going to walk through what I did today. We took a very simple problem, but we're going to do it 3 ways. And we even do the law of sines using, we do the law of cosines using just sines. So that's pretty sweet. Alright, so when I went to college and graduated college, I think all I was paying attention to is, hey, there's equations and there's unknowns. And so, and then you just get into the habit of doing things one way. These first chapter problems in this statics book involve adding vectors together. And they want you to do it, you know what I mean, tip to tail. So we have 700 here. This is our resultant. So we have 2 components. We're just adding those 2 components. They have to equal this resultant. So that's kind of our equation, is vector A plus vector B is equal to vector C. In this case, the resultant is vector C. Vector B is this force F. And then we're already given this. So I'm just going to say this is 700, vector 700. Hell yeah. Okay, so if we add vectors tip to tail, they say do it graphically. We're just going here to there, and then we're going up at some sort of unknown angle. Hell yeah. So, you know, anytime you're trying to find an angle, I got to get into the habit of doing this. See if you can also, you know, do it up here, because check this out. It's like, hey, this is going to be the angle theta. This is going to be the angle theta. Those are going to be the same. But for these problems, what they really want you to do is get this triangle, which is not a right triangle. And then it says, like, hey, what do you know about this? Well, we know that this length is 700, so we do know that. And then we know that this length is 500. And so this is, you know, this is getting into what you're, hey, I mean, well, obviously you're going to use law of sines or law of cosines. Now the question is, which one? And this is where I just started using law of sines. What I did is I came in here and I said, hey, I know this is my hypotenuse. And then, hey, what's this angle? Well, I know it's not theta, but guess what? This is 15 degrees. So this angle right here is going to be theta minus 15. Cool. So why not just use that and get on with life? Well, you know what I mean? This is kind of, you can't get a neat solution unless you know, not have it like this. You know what I mean? Where you have to use, I forget what it's called, but you basically use the a trigonometric identity. And we actually spell that out. But anyway, so this problem is just like, hey, use your trigonometry skills to see if you can find the other angles. Because even up here, it's just like, well, if this is theta, what's this? All I know this to be is just 90 minus theta. That doesn't get me too far. But check this out. If this triangle is a 15-degree triangle right here, I know this angle. You know what I mean? And so, so does that help me out? Hell yeah. And then this is just always, there's a couple like 8th grade moments that you should have with triangles. You know what I mean? One is like, hey, never forget Pythagorean's theorem. I always have to say, hey, don't forget this. You know what I mean? It's like one of those things you learned in middle school. But, man, it's the easiest thing to forget as a student, college student. Anyway, and then the other one for this problem that, man, I just put in my wheelhouse even just a couple weeks ago is just like, oh, no duh. You know what I mean? Is that, hey, if I have this line right here, you know what I mean? And I know that this angle is, well, if this is 15, how do I know this one? It's complementary. And even that is just like, well, if you know this is a right triangle, cool. Then you know that these are complementary. And even sometimes that the professors won't spell it out. So why is this just 90? Why is this angle 90 minus 15? And why is that 75? Well, no duh. A triangle, if you add all the angles together, is 180. So it's a right triangle, so you might as well just start subtracting the 90 first. Cool. And then subtract the 15. And don't you get the same thing? Hell yeah. Because these two things right here is just 90 minus 15. So there you go. So if you have one angle of a triangle, 90 minus it. But you know what I mean? So many people just say, hey, it's complementary, and don't you know that? And then you're just sitting there as a student, you're like, no. So aren't you going to tell me, or are you just going to assume that I know that? So it's a bummer. All right. So hell yeah. But that's not even the one that I forget. If I have a line coming in here like this is called supplementary, I think. Is that, hey, look at these two angles. We have an angle here, which is part of our triangle that we want to know. And then we have this angle right here, which is 75. Well, guess what? We have, this would be 180, right? So we have 180 is equal to maybe 75 plus, whatever this angle is. Let's just call it gamma for now. And then we can solve for gamma. I wouldn't do it that way. The faster way is just like, oh, hell yeah, what's this angle right here? Well, 180 minus 75, and that's this equation spelled out. Get that 75 to the other side, and booyah, we get 105. So now this is where, in this book, they would want you to do law of cosines. They say, hey, I know this angle, and I know an adjacent side to my right and an adjacent side to my left. I know those two. So those are the three things I know about this triangle. So therefore, law of cosines. Okay, so I'm going to try to speed through. I mean, this seems slow. I mean, this is going to be a 3-hour video if I go over everything like this. But I'm just going to show you, kind of walk through like how I was taught as a student at our college. I don't think it was... I think no matter, like, whatever college you go to, it definitely has, it's all up to the professor. If the professor wants you to learn things a specific way, then they're going to do that. But I swear it's just like all the I think there was just this idea, well, and I think in textbooks it's the same. It's just like, hey, find equations, find unknowns, and especially like this, just like, hey, do it a specific way. But then the question is just like, what if you don't see that? What if in your wheelhouse you forgot that if I have this angle, and let's say in your wheelhouse you forgot even to do geometrically add these vectors to even get a triangle, like because as you move on in statics, even just in the next chapter, you kind of throw all this away. So I'm going to go from that place where you throw it away and you just do sum of the forces in the y and the x, and that's what we get. We get two equations, two unknowns. I don't know the force, I don't know the angle. So we're going to walk through here. But even this, my college education would have said, hey, let's solve for one of, we got two equations, two unknowns. Let's solve for one of the unknowns and then just jam it into the other equation. Cool, and then what? Well, and then just throw it into your calculator, because we got two things that we can just graph and just, set everything equal to 0, and then when that equation crosses the x-intercept, then hell yeah, that's going to be the x value where y is equal to 0 is to solving that equation. So anyway, hell yeah. So let's go through it, and hell yeah. All right, booyah. So yeah. So this problem is different than like sum of the forces equals 0. You know what I mean? In statics, you're just like, okay, hell yeah. If I put forces on this joint, like this joint has to resist those forces, you know what I mean? But that's next chapter. That's where I think some of these like very early concepts are like, we're not even worried about, you know what I mean, this. We're just pulling from a point, who cares? But like this is all about resultants. We're saying that, hey, if I have a resultant, or these two forces when added equal 500 newtons, and the problem statement says that it's going to be all in the y-axis. So along the positive y-axis, the resultant will have no component in the x. So then we do that, vector A plus vector B is equal to vector C. So these two components are equal to the resultant. All right, hell yeah. So now I'm just going to hopefully quickly go through, you know what I mean? But hell yeah, so the components. So I'm going to say in the y direction, this vector is going to have a component in the y, and it's going to have a component in the x. This is a cool way to divvy up your vectors. Just put, so this one's going to be this direction, and then this direction. And due to parallelogram, you know what I mean, I can go the other way. So I can also say this is the same thing. And you could also, I don't know if I have any more of these, but you could just do this. Instead of going this way and this way for this component, just go this way and then this way. So that's going to be your two components. So there's 3 different ways to do that. And, you know, each have their benefits. Each are visually useful. All right. So, cool. So we're going to set this as the positive y direction, and this is the negative y. So this is going to have a component that's going to be negative. So we have negative, and this is the sine component. So if this is my angle of 15, I always do like some sunshine and rays, and they shine on the sine component. What that means is that if we have sine, if we write sine of 15 degrees, what does this mean? It's a percentage. Anytime you see in this what you would write would be cosine 15 degrees. And this is also a percentage. Now the question is, percentage of what? Well, it's always the percentage of the hypotenuse. And in statics, typically your vectors are going to be your hypotenuse. You know, we have 700 in that direction. This one could have any direction. We're just saying it's totally vertical. But I don't know. At the end of the day, let's say this one's going to be 1,000. Well, cool. It has, what were we even talking about? Hell yeah, it's got a percentage in this direction, and it's got a percentage in that direction. You know what I mean? So anytime, and I think that's a pro tip. So when I'm looking at equations and I see sine, sine, cosine, I know their percentages. Now, you can't get into the habit of saying, hey, like the vertical, like the y-axis is always going to be sine. But it so that's why I always do the sun shining rays, because that's going to be over here sine. Let's say the complementary angle to this is phi. I could write everything as phi. I could say that this component has a vertical, you know what I mean? So its magnitude is f, so it would be f. And then here's the sun shining rays. This is the sine component of phi, so this is going to be sine phi. But I want the vertical component. Well, that's going to be the not sine component. If this is the sun shining rays, this is the sine component. This one must be the cosine component. I'll have to come up with another little catchphrase. I was just saying, like, hey, if this is the sine component, this would be like, I don't know, the hoodlum in the alley. You know what I mean? Not getting any sun. And booyah. So anyway, so we got, so this is going to be, the after all that, cosine, this is the cosine component, cosine of phi. Okay, now what is that? When we write cosine of phi, what does that get us? Well, it's the percentage of the hypotenuse, but it's only a percentage. It's only a fraction between 0 and 1. So if this was a decimal 0.5, that's synonymous with 50%. That means that this hypotenuse, so how we would write that is like, hey, if this is our hypotenuse f, and then this is, you can see that, hey, just break your hypotenuse up into 2, and you can see that this height is half of the hypotenuse. So cool. And if this was phi, then the sun shining rays, this would be the sine component, this would be the cosine. So cosine phi, this would be 50%, or written just as the ratio 0.5. Now it's a ratio as well, so if this is 50% and that goes to 0.5, always take this number and then divide it by 1, because that kind of spells out what it is for sure. It shows you that this dimension is 0.5 and your hypotenuse is 1. You know what I mean? So that's the ratio. So cosine and sine, thinks percentages, but then the other aspect of it, once you get that percent, let's say it's 50%, always put a 1 underneath it, and we get into that just in a second, where, cool, so let's say I have this ratio of 0.5, and that's going to be associated with the cosine. So this is cosine of phi, hey, is 0.5. Okay, so what happens if we take inverse cosine of this ratio? That gives us the angle, and that angle, you know what I mean, let's say for this one, this is synonymous with a 60-30 triangle. If the cosine of 60 is 0.5, then this has to be 60. If the cosine of phi is 0.5. So there you go. Hell yeah. But then the question is just like, hey, what if we take the inverse cosine of 0.5? What does that even mean? Sometimes you just get this, and we get this part of our problem. Well, do what I do and just always, do I have this written down? Hell yeah, so like right here. So we have the cosine of a number. Always take the cosine of the number and just divide it by 1. So let's do that, just divide by 1. And now it really spells it out. It says that, hey, we have the cosine. What is cosine related to? Well, it's going to be this adjacent and then hypotenuse. So this is the adjacent, this is the hypotenuse. So it shows you the ratio of adjacent to hypotenuse. So this is adjacent, the 1 is the hypotenuse. Okay, sweet. So you can even just write that triangle and say, hey, I got this triangle. It's a right triangle. And I know that this would be my adjacent and this would be my hypotenuse because I just divided it by 1. You know what I mean? Take that number and make it that ratio. All right, sweet. All right, so hell yeah, because this wouldn't have been trivial for me as a student. Because, yeah, we're taking 2 equations, 2 unknowns, but we don't want to just get something gnarly and then put it into our calculator with a solver. You know what I mean? We kind of want to get a unique solution, and that's what we do. And so kind of the foreshadow, when we do this, we get a solution that's synonymous, that looks exactly like law of cosines. We have, you know, a term squared, and so back to what law of cosines would be. Well, yeah, law of cosines ends up this term squared plus this term squared plus the fudge factor. You know what I mean? If this was a 90, hell yeah, there would be no other factor, because sine of 90 would be well, I mean, the way I have it written, because oh yeah, the way I have it written, I don't have it as the law of cosines. I'm still using a sine here, but there should be a cosine here, and the cosine of 90 would be 0. So yeah, that term would go away. All right, hell yeah. So let's go over some of the forces in the y. So I think we did that. We have negative. All right, booyah. So we have so negative 700 sine of 15. Cool. Sine of 15, I mean, we know that sine of 30 is 0.5, and it's linear. So small angle works for sure from 30 to 0. Always use your small angle approximation. And how I do it, I don't even have to change to radians. I just know that sine of 30 is 0.5, so 15, sine of 15 is going to be 0.25. So hell yeah. So we're going to have a quarter of 700, but this is just a known value. So we have negative 700 sine 15, we did it. And then we're going to add the y component of this vector f. Now we don't know its magnitude, so we're just going to say f sine, and now we're going to go back to this theta, you know what I mean? So we're done with phi, that was just to explain stuff. So we have f sine, so if this is the angle, sun is shining on the sine component, so f sine theta. And that's going to be, hey, whatever that dimension f is, but then the percentage of it, you know what I mean? So, and that's what this is. Like, this is a percentage of the hypotenuse based on this angle. Cool. All right, so, and then that is going to, so when we add this one to this one, we have to get 500. Even though this is negative, we're still adding a negative, and then we're adding this one, this component, and that's going to equal 500. Cool. So that's our first equation. Our second equation is summing the forces in the x direction. So we're going to have, I mean, basically, you know how we had vector A plus vector B is equal to vector C? That's exactly what we're doing. Vector A plus vector B is equal to C. But we're doing it in 2 parts. We're saying, hey, AX plus BX is equal to CX. And now we're going to say AY plus BY is equal to CY. So the components in the Y direction have to be equal to the resultant in the Y direction. And now we're going to add the components in the X. So we're going to say negative 700, because this is the negative X axis, this is the positive X. So this will be negative, this will be positive. So we have negative 700 cosine 15, and then we have F, and this is our angle. Sun is shining on the vertical, so this has to be the cosine component. So F cosine, so cosine theta. So this would be F cosine theta right there. All right, booyah. Cool. So we have two equations, and now we're just going to say, hey, cool. So we have two equations, two unknowns. We don't know F and we don't know theta. I'm going to take this equation and I'm going to solve for theta. That's what I have written right there. And so what am I going to do? I'm going to take this, get it to the other side. Cool, so you can see that. And then I'm going to divide by cosine. So cool, this is to the other side. I'm going to divide by cosine. Holy hell. No. I guess I'm solving for theta. So scratch all that. I'm going to get this to the other side, right? And then divide by F. Cool. So this to the other side, divide by F, and then that's going to equal cosine of the angle. I want the angle, so I'm going to say the angle is the inverse cosine. So I did about 3 steps there, right? But get this to the other side, divide by F, that's equal to cosine. Take the inverse cosine of both sides, and then you just left with theta is equal to inverse cosine of 700 cosine 15 divided by F. Alright, so now here is one of the cooler parts of the video. Sorry it takes so long to get to these cool parts. But hell yeah. So what does this say right here? This says, like we have, and do I have this? Yeah, this is cool. It says, hey, we have an angle, so just draw a right triangle. Cool. And this is our angle. And it's associated. So this spells it out. It wants to know. It says, hey, what is the angle when we take the inverse cosine of stuff we kind of know? Even though these are variables, it's like it's totally spelled out. And even if it wasn't totally spelled out, even if this just, we'll get to that in a second, but foreshadow. Let's say this just said inverse cosine 700 cosine 15. Like, well, cool. It looks like it's just equal to a number. So divide that number by 1. And this tells you, this gives you information. You know what I mean? It says, but in this case, hey, we already have something divided. So this says that if this is our right triangle, the sun is shining. This would be the sine component. This is the cosine component. And so that cosine component is 700 cosine 15. And then the hypotenuse is F. Sweet. So we have that. And cool. All right, hell yeah. So now that we have that, here I guess here's where I wrote it. So we have, hey, this is our triangle. This is the cosine divided by the hypotenuse. And so that's the information that this gives you. Cool. Well, now that we know that we have a right triangle and we know two sides, so we don't even have to use the angle. If we know two sides of a right triangle, we can use Pythagorean's theorem to get the other side. So that's what we do. And we say, so we rearrange a squared plus b squared is equal to c squared. And we want to solve for b. So we get a to the other side, so we get c squared minus a squared. We take the square root of that, and that is b. And this is one where, like I got into the habit of, for sure, this happens all the time. So it's real easy if you trying to find the hypotenuse. Let's say, if these are my two sides, it's hell yeah, square them and then add them. So square each of them, add them together, take the square root of that, and that's the hypotenuse. I don't think anyone can forget that. But if I have the hypotenuse in one of the sides, well, I'm going to square the hypotenuse and then subtract the square of the side. So if I can write this quickly, it's just, hey, take the hypotenuse squared and then subtract the square of one of the sides, and then the square root of that is the other side. So cool. So, I mean, the only difference is that, hell yeah, instead of a plus, this becomes negative, and it should be obvious. You're starting with the larger number, the hypotenuse, and then you have to subtract it by one of the sides. So where is if you have both of these sides, well, you squaring them and then adding them and then taking the square root, because you need a bigger number, the hypotenuse. All right, sweet. And then I don't even know if I actually. Oh yeah. And we're jumping ahead. But anyway, so keep that in mind, that because, I mean, basically the next step, the foreshadow, is like, hey, we're going to shove this theta back into this equation, and it's going to be sine of theta. Well, theta is this, so we're going to have sine of inverse cosine. Now, how the hell, so let's move there. So cool, we took this equation, we solved for theta, and now we're going to sub that back into our first equation. So this just goes right back into there. And at that point, hell yeah, you just get it. You get this into there. This is where, hell yeah, you get to the 500 to the other side, and then you can seriously just throw that into your calculator. So let's do that. You know what I mean? So we got negative 700 sine 15 plus, I'm just going to, the f would be my variable x in my calculator, and then we would have sine inverse cosine 700 cosine 15 divided by x. And do I have enough parentheses? And then minus 500. So you would take the 500 to this side, you would set it equal to 0. And what this does is saying, hey, now for this equation to be satisfied, I mean, if you didn't take the 500 to the other side, you're saying, hey, what value of f put into this equation makes this 500? But when you bring the 500 to the other side, it's still the same thing. What value of f makes this equation equal to 0? Well, that's where you can just set this into your calculator as a y equals equation, and then we're going to graph it from, and what are we trying to find? The force. So we're going to go 0 to 2000, and cool. And then so that's going to give me a force. That's going to solve for the force. So I'm just going to go value of 950. Because I kind of know what the answer is. And then I'm going to go right bound, left bound, and cool. So this gives us our force of 960. This is the first time that you could actually, you know what I mean? So two equations, two unknowns, solve for one, shove it into the other, put it into your calculator, get an answer. Cool. And then once you get this answer, you could throw it right back into this equation, type O-law, and get the other angle. But the whole idea of this video is to, you know what I mean? How do you solve this equation? You know what I mean? How do you handle this term? How do you say sine of inverse cosine? Well, we have to take a look at what this is. So, just like when we said, hey, if I have cosine of an angle, that's going to be a percentage. It's also going to be a number, and that number we can divide by 1. So it's a ratio. You know, it's a percentage of what? The cosine is a percentage of the adjacent to the hypotenuse. This would be the adjacent, this would be the hypotenuse. So that's kind of what I have spelled out here. Okay, that's if you have cosine. So what happens if you have the opposite? What if you have inverse cosine of, what would this be? Inverse cosine. Cosine of an angle gives you the ratio. Inverse cosine of the ratio gives you the angle. Cool. Yeah, because hell yeah. Typically we have something like, hey, angle is equal to inverse cosine. So that means that when we do this process, and I say inverse cosine, this is the ratio of that triangle. This is the adjacent component. This is the hypotenuse. All right, so let's use that knowledge and see what we do with it. So we have sine of inverse cosine. So again, work from the inside out, and we have the inverse cosine. This is a triangle where this is the adjacent, f is the hypotenuse. Cool. So we got that, and so yeah, I can't spell this out enough, and I'm probably doing a terrible job. But yes, this ratio says, hey, if I draw a right triangle where this is my adjacent and this is my hypotenuse, and the thing still has to come down and make a right triangle, there's only one angle that can satisfy. So it's back to that same thing. If I know two things about a right triangle, I know everything about it. The only time that you don't know everything about a right triangle is if, like, hey, you just know two angles. So if I have this right triangle where I know theta and then phi, cool. Like, I mean, yeah. It's like, do you know two things about it, though? Because we just said that if you knew one angle, you know, you already know the angle. So this really isn't two pieces of information. So that's how you can sideline that and just always say, hey, if you know two things about a right triangle, you know everything about it. But, you know, every rule has its thing that don't work out. And yeah, for sure, if you know those two angles, well, you don't know everything about it, because this triangle could be scaled up or it could be scaled down. You know its ratios. You know the ratio of the hypotenuse to the opposite to the adjacent, but you don't know the magnitudes of these sides. All right, hell yeah. So how do we do this? So we're gonna say this is the ratio. Inverse cosine gives me an angle. Cool. Of what? Of this triangle. Like, this triangle can't be anything else. You know, if I know an adjacent and I know a hypotenuse, there is only one angle that satisfies to make that a right triangle. All right, booyah. So now it says, and so then you can just, that's why we did this. So let's write that triangle. Let's say, hey, this is the angle. This is the angle of that ratio, and that ratio is adjacent to hypotenuse, and then use Pythagorean's theorem to solve for all three. Why is that useful? Because hell yeah, now we're going to take the sine of this angle. And if we take the sine of this angle, well, that's going to be opposite over hypotenuse. And since we already have this, we already did the work, you know, we know what that is. So sweet. You know what I mean? It's not the friendliest. We got a square root of, you know, a little craziness. But anyway, so we have, but that's going to be the sine of inverse cosine of 700 cosine 15 divided by f. Cool. And again, adjacent, hypotenuse, the angle that is associated with this triangle. I know both sides. So I know, Pythagorean's theorem says I know this side now. Cool. I can take the sine of this angle. It's opposite over hypotenuse. Hell yeah. So I enjoy this method because even I have to go through it at snail pace, but then, like, hey, once I establish that light bulb, be like, oh, I see it now. Then I can go back and quickly do that and quickly see that. But after a few weeks pass, you know, if I see this combo again, I have to scratch my head. You know what I mean? Hey, what is this? This is a ratio, and I'm taking the inverse cosine of a ratio that's going to give me the angle. The angle has to be associated with the triangle with this ratio. And this spells out the component. If this says inverse cosine, this is the adjacent, and this is the hypotenuse. If this said inverse sine, well, yeah, then this would be over here, the sine divided by the sine side divided by the hypotenuse. But cool. All right, so that's where we get sine of this angle is this divided by the hypotenuse. So that's what we have right there. And it's f sine of this angle. So we have this divided by f, and then we multiply it by f. Those f's cancel. Hell yeah. So, all right, let's see what we're left with. I got to juice up the battery. Catch you on the flip side. All right, hell yeah. So now I think we're about at the plug and chug, but there is one more identity. You know what I mean? Because once we have this, I mean, if you've done these problems, you know what I mean? Obviously, you're just going to, well, factor out that. And, I don't know, like, you still have to solve for f. I mean, you still do things. That's the idea. Is like, I don't want people to have to know tricks. I don't want myself to know tricks. I just want to be like, hell, let's do some grinding. So I want to solve for f. How do I do that? Well, I'm just going to get this to the other side, and then that's going to be over there. And then, ooh, I better square both sides. Once I do that, then I can get this to the other side. And then I can take the square root of all that, and that's going to give me f. So that's kind of what we're going to do. We're going to get this over there. So cool, that's over there now. The f's canceled, so we just have this. Now I'm going to square both sides. Now I do go over my style of squaring. So if I do, now I'm just gonna for visuals show you that we're squaring this. How I square it, I know I'm gonna, because you're gonna have FOIL. I mean, you're gonna have, I'm not gonna write it, but you're gonna have this times itself. So you're gonna have 500 times 500. Cool, and then you're also going to have this times that. Those are the two obvious. So if I have this squared, I know I'm going to have a 500 squared. And so that's this. I know I'm going to have this term squared. Now, it's going to be, I have to square both. It's a product of two things. So I have, you know, and you could write this if you're not, yeah, two things. If you don't like to write sine squared like this, don't. You know what I mean? I didn't for the first about 3 years, or at least a couple, I would say 2 years getting back into the rhythm of things. I'd be like, hell no, I don't like that. I like, and so I would, but anyway, if we're squaring this, you just write it as 700 sine 15 all squared. But just know, like, hell, this is two products, so we're going to have 700 and then a product of sine 15. And I can write this squared times that squared. That's the same thing. So that's why we have this. And then just, heck yeah, if I have sine 15 squared, yeah, just by, this is just the generic way to write it, because it saves on parentheses. And even though this is totally spelled out, like you would never mistake that you're taking sine of 15, whatever that is, you know, I mean, after a couple years you forget even what that even means, but it, you know, not today, because hell yeah, sine of 15, that's going to be a percentage, and more importantly, it's going to be a ratio. That's going to be a number too. It's going to be a number divided by 1. That's the ratio of the opposite over the hypotenuse, and that's indicative of a triangle with this angle of 15. So hell yeah. So if I have an angle of 15, for sure, this side is going to be in proportion to the hypotenuse. Cool. And sine of 15 for small angles is going to be 1/4, 0.25. All right, hell yeah. And so cool. So if I square this, this squared plus this squared, and then we just have that second term. Because if I had a plus b, if I have a plus b squared, I'm going to have a squared, and then b squared. But then I'm going to have a times b plus b times a. So I'm going to have two of these. They're the same term, so I have 2 ab. Cool. So this is how I do it real fast. So that's how I have it spelled out here. And even just writing it like this, a squared plus b squared plus, well, now we're going to just multiply both of these. 500 sine 500 times 700 times sine 15. And then I'm going to have 2 of them. So that's why I put this 2 right here. Cool. But anyway, so I know that in advance I'm going to put the 2 out front. And so this is how I did it. 500 squared plus 700 squared sine squared 15 plus I'm going to have 2 of 500 times 700 sine 15. I don't like to do everything in parentheses, but for sure just a couple things in parentheses. I could have done that. That's still visually cool. Because this is tied in with, you know, this is a hypotenuse and this is a percent. Like this term is for sure. That's where reading equations you can, you know, again go back to, like, what is this 700? 700 sine 15? Hell yeah, that's that component. Alright, booyah. So, hell yeah. So we have that. So we have, that's all we did. We just squared both sides. The square root goes away. Alright, let's see what we have. So we're trying to solve for f squared. Cool, so now we need to get this to the other side. And that's what we do. So we have basically 500. I got this term right there. And then I have the 700 squared sine squared 15. And then I'm going to add 700 squared cosine squared 15. I just got these two terms together because I kind of knew what we're going to do next. You don't have to. I mean, there's nothing saying that you couldn't. We're already down to f. Like, just seriously, just take the square root of it and get on with life. I mean, Like at this point, it's not even useful to know that sine squared 15 plus cosine squared 15, to know that you can factor this. You know what I mean? Both the magnitudes on these, but yeah, both the magnitudes have to be the same. And so I can have 700 squared, and then I can factor sine squared 15 and cosine squared 15. So putting this in brackets is the same thing as foiling this to both terms and getting that. So, alright, booyah. And then we just know that sine squared of an angle plus cosine squared of that same angle is 1. And why is that? Well, if I have this angle, and this is a hypotenuse of 1, here's my angle, let's say I know it, whatever. This length of this side, and it doesn't even matter. No, I guess it does, yeah. The length of this side is the hypotenuse, 1 times sine theta. So I'm just not writing the 1. And then the length of this side is 1 times cosine theta. Cool. So now, visually, like these are lengths. This is 1, this is sine of that angle. And then, so just using Pythagorean's theorem, hey, this squared plus this squared, square root that is 1. Cool. So that's the same thing as this squared plus this squared equals 1 squared. Cool. Well, that's just 1. So cool. This squared plus this squared equals 1. So that's kind of the, you know what I mean, the most known trig identity on the planet. Cool. But I was just showing that you don't even, who cares if you miss that? You know what I mean? Other times, hell yeah, you want to find this because there's just a lot of junk and you're trying to simplify. Alright, sweet. So cool. So this factors out to 1. But a mistake you could make would be like, oh, isn't these two terms just 1? Well, no. You can't add these two, you know what I mean? You have to do this process of like, hey, foil, like a unfoil? I don't know what you'd call that. But factor out 700 squared, and then you have this term. So this is still, and it goes to this. Like, hey, this side plus this side does not equal the hypotenuse. But because of the, you know what I mean, fancy videos on YouTube, maybe showing that these are squares or, you know what I mean, who knows what's going on, is that, well, that's exactly what's going on. Well, I mean, yes, this length squared plus this length squared is this length squared. So it's just kind of the fascinating thing about right triangles. I should probably, I don't know, you know what I mean? I mean, is there anything else there that's useful than to, I think it's a useful visual, I mean, yeah, I should actually do a visual proof on that just to, I don't know, that brings up the concept of, though, like, hey, what is a proof? It's almost just another way to, like, double check that your answer comes from, like, a logical foundation. But still, a proof has to come from other simple proofs that are very obvious and evident. You know what I mean? But then those have to come from, everything gets back to, like, hey, can you prove that the numbers are equally spaced? You know what I mean? Stuff like that. I don't know. So, but I am, at least I know the lingo enough to be like, hey, yeah, there's proofs, but you're building on a foundation of logic that came before that. Sweet. All right, so hell yeah. Just, yeah, this side squared plus, you can't add these sides to get the hypotenuse, but if you square these sides and then add them, hell yeah, that's the hypotenuse squared. Cool. All right, so, yes, this just becomes 700 squared, and now we have 500 squared plus 700 squared plus that extra component. And it's 200, 500 sine, 700 sine 15. And heck yeah. Alright, hell yeah. I'm glad I took a little break because I just wanted to look at this. I knew it's related to law of cosines, but that definitely ain't a cosine. But what does this say? What did we just talk about? We said that if we have a right triangle, you know what I mean, a squared plus b squared is equal to c squared. Cool. So this, isn't this a squared? Isn't this b squared? And then why do we add an extra? The only way that we would add an extra is if, like, hey, this angle is like that. And so we're still down here, you know, we're using this 15 degrees. Oh, yeah, this is interesting. I mean, I would have to come back and look to see where this 15 degrees is associated with this triangle. Because this ain't 15. No, this is the 15 degree triangle, and I'll probably have to print out some more of these sheets. But yeah, that's kind of fascinating. But just in general, what I saw from this is like, hey, because we have this component, like these two sides, this 700 and this 500, do not make a right triangle. Because we're going 700 plus 500 plus something extra, which is harder to see with law of cosines. Because if this law of cosines, usually this is a minus, and then your cosine, for this problem, my angle is going to be 105, so I have an angle of 105, so I'm going to have cosine of 105. Well, how does, so this is a good refresher. If you have angles that start from the x-axis, and we're going to say, hey, this is positive, so this is 30, and then, hey, this is going to be angle, and this is going to be the positive direction. Cool. This has a sine component that's positive, and this has a cosine component that's positive. It's in the x. Positive x, positive y. This is the negative x. This is the negative y. This is the negative x. So if I have an angle of 70, cool, still, vertical component's positive, this component's positive. But then once I get past 90, let's say just 110, now this angle is still 110. I can take the sine of 110. That's still going to be this percentage of this hypotenuse. So I still have a hypotenuse. I still have an angle. And this is going to be the vertical component. It's going to be positive, but if I take cosine of 110, look at this. It's in the negative x direction. So I think visually, I think it's dumb to just be like, well, this is the take-home point for this whole thing. Like, I refuse to do law of sines, and I refuse to do law of cosines like you would the quadratic equation. I refuse to do the quadratic equation. I hate it. You know what I mean? Why would I want to say is x is negative b plus or minus the square root of 4ac, I get it all wrong, b squared minus 4ac divided by 2a. Now I might write that as a check on reality, but I'm always going to complete the square. You know what I mean? And you get a nicer number, especially if you do it by hand. Because these terms are squared, oh, hell no. You're inside the square root, just goes huge numbers. And it's really difficult to do it without a calculator. If you use this, completing the square is way better. Same thing, if you know that, hey, sine is going to be, you know, sine of 45 and sine of 135 are going to be positive, but cosine of 45 is going to be positive, but then cosine of 135 is going to be negative. So hell yeah, if you take cosine 135, hell yeah, that's going to be in the negative direction. But that's why when you have if this is 105 and you're doing law of cosines, like how do you actually draw that? Well, we'll get to that. Well, we have a very nice drawing of it, so let's just flip to that page. So we have this components are 500. This components are 700. No, that's still not even it. Here it is. So here's law of cosines. So we have this is our angle, and then this is 700. And then this component. Sorry, yeah, it's kind of weirdly drawn. But this component right here, from there to there, is 500. So I know this component, and I know this component, and I have this angle of 105. This is the tried and true. This spells law of cosines. If you have an irregular, not a right triangle, and you know an interior angle, and you know this side and that side, adjacents, well, look at this. Like, I don't know this angle, and I don't know this angle. So this the sine of this angle is in proportion to this length, and the sine of this angle is in proportion of this length, and the sine of this angle is proportionate to that length. But I don't, like I'm missing that ratio. So this to that, missing it, and missing it. So that's where you take the law of sines. And you just do it as an equation, but why would you? I think it's harder to do. It's easier to set up when this angle is bigger than 90, because it's just visually you're like, oh, I'm just taking this, and well, you have to extend it out, and then come down and drop a 90. Law of sines would be the opposite. I'd be like, hey, this is my hypotenuse, and this is my hypotenuse. So let's make right triangles right here, and then I know these interior angles, especially if I know those two interior angles. And that spells out the law of, well, and I don't need to know both of them, because I'm gonna relate this sine. If this is the angle, sun is shining on the sine component. 500 sine of this angle is this. So let's say I don't know what phi is, but I do know what theta is. So 700, and then let's say, well, this is theta, so. Well, let's just call this gamma. So for sure, let's say I know gamma, and then 700 sine of gamma is this. I don't know phi though, so I'm going to say that's going to equal 500 sine of phi. That's the law of sines. But just how to draw it though is like, hey, I have this triangle, and you know what I mean. Law of sines, you're going to probably do that. You don't always have to do that, because this triangle doesn't have to be obtuse either. It could be, this triangle could be like this, where I don't know. Yeah, if I know this side, yeah, how would this work? Yeah, if I know this angle and this, hell yeah, this is I've got to get a 90, and so this is my sine component. I'm only gonna go over like what I've done, because else I'm just gonna say wrong things. Anyway, for this one though, if your angle's larger than 90, you're gonna extend this out, drop down a 90 degrees, and so yeah, and it's a little bit tricky, but and then you go off this angle though. You could, like, the easiest way is to like not go off that angle. So what I did is said, hey, this is my supplementary angles. Like, this is a straight line. So 105, I know what this is. 180 minus 105. So this is 75. I know this angle. I know a hypotenuse. And so heck yeah, I know my cosine component. So that's going to be x right there. And then so I know this full side. Because what are we ultimately trying to find? We're trying to find this dimension right here. Like in the problem, it says, hey, what is f? So f is what we want to know. And you're basically turning this into a right triangle. So if I knew this whole side of this right triangle and this whole side of this right triangle, I could square those and add them, take the square root, that would be f. Sweet. Cool. And so, but I just know this hypotenuse to this new triangle that I made. So cool. So this is going to be the sine, 500 sine of 75. This is going to be 500 cosine of 75, but I have to add it to this length of 700. So I'm going to have this squared plus this squared, square root that, and that's essentially what I have. And so that is the law of cosines. So I'm glad I showed you that first, because what I do after this problem is, well, it's kind of cool. We do the law of sines, because I did not see that. Putting this geometry together, I didn't see that, oh, no duh, I know this interior angle. And so, yeah, it's kind of fascinating. So stay tuned for that. Alright, sweet. So first one, basically done. We did 2 equations, 2 unknowns, learned a bit about triangles, got it down to here. See how this is similar to law of cosines, and I could get this identical. Like literally, this is going to be spot on identical to the answer for law of cosines. So here is 700 squared plus 500 squared plus 2 700, 500 cosine 75. But this is typically not even how you do the law of cosines, because I used this 75 and I didn't use this original interior angle. So that's why I do it one more time and use that. If I'm using, so let's talk about that. If I use this interior angle, I know that this is my hypotenuse, but now I'm taking 500 as my hypotenuse. So let's do this one first. So I'm taking 500 cosine of 105. Well, that's going to give me a negative, it's going to give me a negative number. So this number right here, let's say it's 500 cosine of 105 is a negative number. I have to add it to this. So I have to go 700 minus 500 cosine 105. Because this is minus, like when I put this in my calculator, this part gives me a negative number. The only way to add these two up is to have this negative right there. So that's kind of the bummer about law of cosines with an interior angle greater than 90. Because you have to, it feels like you're subtracting something when you're really not. You're subtracting a cosine of a cosine greater than 90. So this is a negative, so it's a negative negative. So this is, so that anytime you see a cosine now, cosine equations, I'm just going to do this for myself. I'm going to be like, oh, so now if I see plus, plus, and then this is an addition term. This is for sure adding a bigger piece. And the only way to do that, so this is going to be one side, the other side. If this is 90, hell yeah, if there is no other piece, but we do have another piece, so that makes this longer, this hypotenuse compared to that hypotenuse. Because of just that little extra, you're adding that little extra component in, and then you're squaring it, to this. Cool. All right, sweet. Alright, so that kind of goes over that. That was pretty decent. Probably not. But, yeah, we're doing pretty good. I guess this is exactly how I thought it would go. I don't know how to say just one thing and then just move on. But, I just don't want to get frustrated. But, no, I think we're doing pretty good. So, yeah, so now the meat and potatoes of what we did. And I think you get the idea. We have this 700 down. Resultant of 5 and a force just in whatever direction. So I do blow this up. So it's actually really good right here. So I have this is the 700. This is the 500. And yeah, that's the only thing. I'm starting from this point right there. So I'm actually starting from my origin, dipping down, and then going back up. And then that. So that's the only thing that's kind of interesting. This is the origin right here. And so 700 down at 15, adding, this is force F, back up at an angle to the horizontal, to the horizon. This is that angle. All right, so now I'm going to, and this is the resultant of 500. This is 500. So this is what I'm going to show you, how I just stumbled across law of sines. So I'm doing law of cosines with law of sines. You know what I mean? I'm taking a problem that should just be done with law of with law of cosines and using law of sines. All right, so this picture is really small, so let me come back to here. So what I know is I know this. I for sure know this, and then I was just like, well, hell yeah, let's do law of sines. And I'm going to darken in the ones I know. So this is 500. Know it. This is 700. Cool. And this is where this problem is. Like, I guess it's interesting because this is one component, this is the other component, and this is the resultant. And this shows you that, yeah, let's talk about this because this is really fascinating. With these adding components that equal the resultant, you're like, hey, sometimes these components can be way longer than the resultant. The resultant isn't necessarily a hypotenuse. And these can be way, way long. And so one component of that is like, I'm going to do this. Let's say you have a car stuck in a ditch. You know what I mean? So here's a car. Cool. So you have a car, and then you have two trees, one right there and one right there. And then this is cool. This is cool because I'm gonna throw you for a loop. Probably not, but I'm just like, hey, and yeah, and let's say you have a rope. Let's say you have little pulleys, and then you can attach ropes to like, you know, something on the car, like right there. So I'm going to take a rope to that point and a rope to that point. And then these just go around pulleys. And so it's just a change in direction. So I'm just going to add some people. And a person is going to pull on that side, person's going to pull on that side. This is just a change in direction. It's equivalent of them just pulling. I should just do this with two people. And they're just pulling that direction. So if that's another way to visualize it, you know, forget the tree. But two people are going to pull in that direction because they heard that vector pull. Hey, if you have like this, like a tight line, and you should get mechanical advantage. But this would be the opposite, drastically the opposite of this. Let's say just, and this is the other thing. Like I did a video of like pulling nails out of, like, just really old nails out of you know, this old house, and just with a claw hammer. Well, at the end of the day, that nail to come out of like that old wood is just hard as, yeah, everything's just really hard. All it takes is a force. You know, at some force, that nail's going to rip out, or it's just going to you know, break in two. But as long as the strength of the nail has got some rigidity, it's just got a hell of a lot of friction, you know, friction force resisting due to the pressure, and then a coefficient of friction and a normal component. You definitely have a normal load on that nail, and a coefficient of friction with metal and wood. And so, hell yeah, you get friction force that you need to overcome. But still, you still just overcome it with a number of force. It doesn't matter how you get that number of force, you know, cool, that's the number of force you need. So let's say this car, you need a yeah, let's just say, you know, let's say this is very similar to because I'm going to do the analogy of a slack line. So two trees, and then a person. And then, hell yeah, cool. And then, so let's say these angles are the same. So this angle right there, same as this angle. So we have a really, so this, I didn't really draw it very good because draw the angle too big. But yeah, let's say these are really shallow angles. But let's say all I need on this car is like, what does this person weigh? Like 200 pounds. So let's say I just need 200 pounds of force. That is the number I need. I need 200 pounds of force to get this car unstuck. And so cool. And how and I sorry I drew this horrid. You know what I mean? Like this has to be a really shallow angle. So if this is just a really shallow angle like that, just hardly any at all, and we got two people pulling on those ends. It's the same thing as a slack line that's really tight, where this angle is just also really small, really small. Hell yeah, but it just shows you like this is maybe more obvious. It's just like, hey, I put a force down of 200. This is where statics gets you after a couple chapters. Just even the next chapter, they're just like, well, yeah, the only way, like you're a mass that you weigh 200. The only way to actually keep you, well, and the reason you do have a force on you is a force of gravity. So you have a 200-pound force of gravity attracting you to the earth, and that's pulling you down. If you were just floating in outer space, but then there was this force, you know what I mean? Let's say a big planet over here that was so massive that's the same thing. It's going to, like, there's going to be a force and what does a force do? It accelerates you, but it definitely moves you. If something's holding you here in outer space, and then let's go. Your velocity goes from 0 to starting to accelerate. You know what I mean? And so that's what would happen if you're a mass on the Earth. So in general, yeah. Anyway, so yeah, you would need, because you are not moving. That's the whole idea of statics. The fact that you are not moving, there has to be a force that's equal and opposite. And the only place to get that force is on this webbing due to a slack line. And if this webbing has vectors in this direction, it's only the component, which is really small because this angle is tiny. It's only the vertical component that's actually holding your load. And so you can get easily a 10x. The wild thing, though, is even if you have like if I have a welded steel bar, I want to do this scenario where if I have a, like what's the minimum diameter, you know, if I just take a straight section, weld it to, it'd be really difficult to find two rigid walls that you could do this experiment with and then go stand in it. Well, sure, like steel can only lengthen, like 1 meter of steel, 1,000 millimeters, can lengthen 0.2%, which is to 1,002 millimeters. But that's only until it starts to kind of yield like taffy. But it can maintain its strength until it can get from 5 up to 5% of its length. Sometimes 10%, sometimes 30% if it's a really good specimen. But for sure 5, you know what I mean? Most times 5 at least. So hell, this thing can get up to, this is a kind of a fascinating to do just on the spot. If 0.2% was 2 millimeters, 5% is going to be 50 millimeters. So now I have a length of, this overall length is going to be 1,050 millimeters. And so what, this is like one of those, you know what I mean, viral YouTube videos. It's like, well, if that's the case, if steel yields after I welded this bar and then stand on it, could I stand on it? Or when it does yield, what's the angle? You know what I mean? That's kind of the more fascinating question. And I'm just going to result to the calculator, because one thing that goes underlooked is Pythagorean's theorem. We were saying this was a distance of 500 and 500, and now we have a hypotenuse, which is now 525 on both sides, which add up to 1,000. So now what would that be? Well, we're going to take that square root of 525 squared minus 500 squared. So we just use that equation that, you know, I was saying for sure have in your wheelhouse to memorize. If I have the hypotenuse and I have the other side, how do I get the side I don't know? Well, I'm going to take the square root of the hypotenuse squared minus the other side squared. And booyah. So this other side squared is 160 millimeters. So that is really fascinating to me. Did we do something wrong? You know what I mean? Let's talk about it again. If I have 1,000, if I have a 1 meter steel bar, it can lengthen 5%, which is 0.05. So it can lengthen 50 millimeters. Cool. So this is a fixed distance of a meter. The steel bar lengthens, let's say like a triangle. And so this one's going to be 525 plus 525 is that 1,050. So I'm going to take the square root of this 525 squared minus 500 squared, and I get 160. Wow, that's incredibly surprising. If only bridges were like, you know, could stretch like taffy. I was always fascinated, like if you can just build that into the design, because like, you know, cool, you have a bridge like this, but let's say if your bridge kind of starts to collapse and then turns into, you know, just like a swing, like a swing set, hell yeah, it can just hold way more load. But yeah, you would have to have, yeah, it'd be fascinating. I'm sure some structures are able to not fail catastrophically. But wow, so now we can find this angle. That's going to be the inverse tangent of that answer divided by our side, 500. And so our angle is 17 degrees, where, I don't know if you're familiar with setting up a slack line, but you need at least like a 3 degree angle. Let's do it. Let's go, let's do the sine component. Sine of 3 degrees is going to be 0.05. We're going to invert that, and that's going to be a 20x multiple of the hypotenuse. So whatever, if you have 3 degrees, whatever the hypotenuse is, you're going to see 20x. And so, yep, so what would be a 10x? You would be inverse sine of 0.1. Yeah, so you're looking 5 degrees, 5, 6 degrees. So you set up a slack line, or like a zip line. You know, it doesn't, I guess the take-home point, it doesn't require very much angle for this to go from infinity to just be like a 10x multiple. And, you know, with a what do they call it? I've said it a few times, with like the pulleys and then the zip lines. So if you have a zip line, hell yeah, you can make, well, 2 things. You can make the angle, I guess there is a couple things, you know what I mean? Because if you pre-stress the steel, you know what I mean? Like if you stress this steel where it can only, you know, you've already lengthened, it can lengthen 5%, and let's say you already lengthened 4.9%, and it can only lengthen 0.1%. Well, obviously, you know, that's going to snap. Because, hey, this angle can't sag. So there is that when it comes to setting up slack lines. You're already like pre-tensioning it. But even with the tension in a slack line, you can calculate that with gauges. So in general, webbing can take 4,000 pounds, and you have 2 lengths that are trying to support 200 pounds. You know what I mean? So you're going to have, oh, never mind. But hell yeah. So what would you, yeah, what would be the minimal angle on this? So, yeah, these are good side problems to do because it tells you that you have a good understanding of sines and cosines. So if I have this component to be 200, but this is going to be maxed out. Let's say it's 4,000. Cool. So, and this is not 200. This is 100. Each of these, even though it's just one piece of webbing, you know, I have a pivot point here. So it's like, it's the same as 2 pieces of webbing coming off underneath my feet. And so there's got to be 100. The vertical component of this piece of webbing has to be 100. The vertical component of this piece of webbing has to be 100. Okay, so what would this angle be for this webbing to break? Well, I would have to have a, so what does, if this is my angle, what does sine of this angle mean? That's the percentage of this height to the hypotenuse. So I would have, and then, so I know that my percentage is 100 to 4,000. So sine of the angle is going to be 100 divided by 4,000. So that angle is going to be inverse sine of 100 divided by 4,000, which is 1 divided by 40. So inverse sine of 1 divided by 40 is 1.4. So yes, if you, it would be very difficult to do because, No, I guess it's not. If you tension, how does this work? Oh man. All right, yeah, some of these are hypothetical. So you're just like, okay, so if I have this setup where I stand on this slack line and I want to generate that angle of 1.4, what I would do is I would pull tension on both those points until this angle came up. Like obviously if the slack line is loosely attached and I stand, it's going to slack way down. But I'm able to pull on both ends, let's say, and so I can pull on both ends, and this angle is going to reduce. And the second it reduces to 1.4 degrees, that's when you're going to hit the yield of the nylon, but let's just say the second you hit the yield is where it breaks. You know what I mean? So because I always like to think of that concept, even though things do like yield and can reach and can elast and then inelast, like plastically deform. I like to have in my mind that when you reach that plastic deformation, like lives have been lost and jobs have been lost. You know what I mean? You lose your job and you have lost lives. And so, yeah, just kind of from that perspective, I consider that just mentally, that's where things break. If you're taking something to the deformation limit, you know, that's kind of breaking in my book. But there's a lot of cool problems where actually you have to take something to that deformation. But if you take a steel bar and stretch it 2 millimeters, it still has its full strength up to 5%. You know what I mean? So it's not, it actually isn't where it broke. So there's plenty of indeterminate problems where you can take it from 2 millimeters to probably 10 millimeters. You know what I mean? And that it's designed to do that. You know what I mean? Don't take it to 50 because that's when it's going to break. But, you know, take it to a quarter of that, and you might be within that window of being like, sure, that's totally fine. And cool. All right, that was a tangent. But yeah, that was good though. All right, hell yeah. So I think we're on our home stretch. We're going to set this up with law of sines, but we're going to basically identify, or we're doing law of cosines with law of sines. All right, so we need to figure out what angles are going on. I guess that's where man, and I really bummered up this page. That's all right though. So this was that 15-degree angle, just right here. And this triangle we know everything about. It's 700. And so I was just thinking, well, I get this. I've set that up. And so, you know, I know where law of sines comes from. It's saying, hey, if this is a hypotenuse, and then I come down here to a right triangle, and then that also makes a right triangle with this one. And I know that hypotenuse. This is 700, this is 500. Sweet. So let's find this. This is the sine component, so that's going to be 700 sine of this angle. But this angle right here is going to be theta minus 15. So it's theta minus 15. You know what I mean? So that's this angle. I didn't think anything of it, but that's going to be 700 sine theta minus 15 is this length. And then this is going to be 500 sine of 90 minus theta. Now, I was smart enough to know for this one that, hell yeah, like that should be red flags. If I see 90 minus theta, you know what I mean? It's just like, well, that's the definition of complementary angle. You know what I mean? So if this is a right triangle, this is 90 minus theta, well, this has to be theta. And let's do that, because let's do it long way. This whole triangle has to equal 180, so I'm going to go 180 minus, okay, 90 minus theta is going to be 90 minus theta. You got to do that, though. Cool. And then, so it's going to be 180 minus this, so 180 minus this, minus the 90 from the right triangle, and that's going to equal this angle that we don't know. So this one's going to be 180 minus 90 plus theta minus 90. So, yeah, so it's going to be 180 minus 90 minus 90. 180 minus 180. So we're just left with theta. So cool, that angle is theta. So that was kind of a couple ways. And just, if this is 90 minus theta, well, this, because we have a right triangle, is 90 minus theta. And so we have 90 minus 90 plus theta. Cool. We just get theta. And if I knew that, and I have this as my hypotenuse, well, now I know what this is. It's just the cosine. It's the, like this is, sun is shining, this is the sine component of theta. So 500 cosine of theta is that component. Cool. So if I said 500 sine of 90 minus theta, which I have right here, 500 sine of 90 minus theta, I just know that that's cosine. So that was kind of a good little tip and trick. All right, so now what do we do with this is I've already watched I've already watched 2 videos. They were for sure spaced apart. Like, this is one of those things where if you have this and you're trying to get it in the form of sine theta and sine 15 and cosine theta and cosine 15. This is kind of the forms that you're getting it into. But if you have it like this, there is no term that's sine theta minus 15 or sine theta plus 15. So you're getting rid of those. So you're taking both of those 2 scenarios. We have theta minus 15. And you're just getting it in terms of theta, sine theta, cosine theta, sine 15, cosine 15. So that's kind of the general gist of when you see this, you're like, ah, damn it. You know, you probably got to watch a tutorial. All right, so we're going to, so how I set this up was just like, well, I was like, I'm chill. You know what I mean? We can figure this out. And so I tried to divvy this up. So here's my, I'll just kind of go over my techniques. So I do know this hypotenuse. So I just start checking stuff that I know. I know this hypotenuse and I know this angle. Well, hell yeah. That's 2 things of a right triangle. I know everything about this right triangle. So I know this side and this side. All right, so let's move on. And I guess I knew enough to like, hey, this was theta. So this whole thing is theta. This was, I guess I have this gamma right here. This one's going to be theta minus 15. So that's that part. That I guess I just have as gamma right here. Yeah, I set this triangle up as gamma, beta, alpha. Alpha is 105, so we actually figured that out with geometry, so that's pretty sweet. We said that beta is going to be 180 minus alpha minus this. So yeah, we have yeah, so we know what beta is. Yeah, we already knew what well, yeah, so we know what 90 minus theta. Cool. Yo, I need to go back to a better drawing of that. Yeah, so we knew 90. We knew what this angle was, 90 minus theta, and we actually probably got that from adding up those angles. I knew this interior angle. I think yeah, it's kind of fascinating how I actually did that. Anyway, all right, so, but yeah, having to, so I have this hypotenuse, I know those 2 sides. I'm just trying to think of why I drew that point in. Oh yeah, and this was the whole idea. I was doing sines, so like, hey, this was, so yeah, so let's do it on here. So yeah, because that's why I did these. Yeah, this was just a little bit cramped, and I probably even drew a second picture anyway. So here's the first thing that I did. I said that this was 700 cosine 15, know it. I said this was 700 sine 15. Cool, I know that. What I'm really interested in is this one. And so that's where that's where I was just like, well, how do I get this one? And I could say, hey, well, if I knew this angle, well, this is the angle I do not know. This is the angle that's theta minus 15. This is what we're trying to get some other way. Cool. So I started in reverse. I said, hey, if, you know, I was using law of sines to begin with. I was saying, hey, this is the sine component of this triangle, which is a right triangle. This is a right triangle. So these are the 2 sides. This is the hypotenuse. So I said, hey, if I know this hypotenuse, and I just said it's, you know, box double star, then I can know the final thing I want to know, which was box triple star. I was just trying to figure out different ways to label things without just using letters, which seems maddening. That's why in this one I use numbers, and I'll go over that. Okay, so even just going from here to there, like, man, it always, like, it's like a head scratcher, but nah, like, I know the hypotenuse, and I know the angle, and so how do I get, the sun is shining, this would be the sine component, this is the cosine component, sweet. So this is going to be the hypotenuse, cosine of the angle, hell yeah. So that's going to be triple star. So triple star, the thing that I want to know is this length, don't know it, but it's the hypotenuse, cosine of that angle. Cool, so now, then I said, it's like, well, how do I get this length? Well, I said, well, is this part of a right triangle? Hell yeah, it's part of this whole right triangle right here. And I was just like, well, how do I get this whole thing? And is that even what I did? Maybe not. Let's see. Let's see how I did get this. I don't even know where this. Oh yeah, so I have this length. Okay. Oh yeah, fascinating. Well, I probably could have done two different routes to go. I could have easily said, hey, this is going to be this component minus this, which I do know. But then I just need to figure out what the hell that component is. But I have, yeah, this is interesting. But we still want to use things that we know. All right, yeah, how did we solve for this one? Oh, okay, got it. I keep confusing myself. So the angle that we do not know is just this one. This is that theta minus 15. It's kind of useless to us. That's why we're trying to get it in terms of other things. But I for sure know this full angle. And so I know theta, well, just as a variable, you know what I mean? But I do know it as a variable. And then I know this side. So this full right triangle, even just right there, I know one side and an angle. I know everything about this triangle. And so here's where I need to get better. It's just like, hey, I could solve for this side. I could solve for this side. It doesn't really matter. And I think I did this one. I don't know if I did it in two parts. But yes. How do you go from a side, which should be smaller? The side should be smaller than the hypotenuse should be bigger. Well, you're going to take that smaller number, 700 cosine 15. It's related to this angle. The sun is shining. This would be the sine component. So this is the cosine component. Cool. So it's going to be related with a cosine to the hypotenuse. And I'm just going to divide it by cosine theta. And the reason is that this cosine theta is always a number between 0 and 1. It's always a smaller number or a fraction, 0.5, 0.7. And when you divide a number by a fraction, you get a bigger number. So there you go. I'm taking a side. That is my strategy to take a side and get the hypotenuse. So I'm going to say, hey, 700 cosine 15, here's my angle. It's the cosine part, so I'm going to take this divided by cosine of that angle. So that's what I do. And I know that the cosine of the angle is a percentage, a smaller number, and a number divided by a fraction between 0 and 1, whatever you call those, is going to boost that up. It's going to make that numerator, just that number bigger. Cool. So that's how I get that term. All right, hell yeah. So this was working backwards. Like I wanted to know this. I said that if I knew this, it was going to be hypotenuse cosine of the angle. Cool. So how do I get this? Well, I said that I don't even. That's weird. How did I get that? Oh, well, I said. Oh man, I think I mixed up terms here. Because this is 700 sine 15. So, oh, I see. Yeah, this is kind of interesting going back and forth, but, yeah, let's just do this one again. So I want to know this just by itself, and that's what it is. So I'm going to say, hey, I really need to know this full length, and that's where I just don't know. I'm just going to call this A, just so it's different. So I'm going to say this is going to be A minus 700 sine 15, the sine component of 15. So that's kind of what I have here, 700 sine 15. But this component A, I don't know it, but I do know what this component is. So this is where I did two steps. I said, well, hey, let's get this, and I guess I'm going to call that theta. This whole thing is box with an asterisk. And so I'm saying that, yeah, this, we just did it. It's going to be this component divided by cosine. So I think I'm back on board. So that is this. Cool. So now how do I get this? Well, I'm going to take this as my hypotenuse, and then this would be the sine component. So h sine theta is this component. That's going to be A. What I have here is A. So there you go. So this sine theta is this component. And then I'm subtracting. So I'm taking that component A, and then I'm subtracting that. Brutal. But I could have just, yeah, and then I'm not going to go over it again, but in the end I do show you that, hey, if I just know this, well, how is this related to that with tangent? But sometimes I just, I easily can do this in my head. I can say if this is the side, how do I get to the hypotenuse? Divide by cosine of the angle, which is dividing by a smaller number. If I was trying to get to the, if I was trying to relate these two, well, I would have to say tangent of the angle is this A opposite divided by 700 cosine 15. And what do I want? I want A. So I would have to do it in two steps. So 700 cosine 15 tangent theta is A. And so same thing. Yes, it's the same thing because here I'm going to have 700 cosine 15 divided by cosine theta multiplied by sine theta. So this becomes tangent. So that's the same thing. 700 cosine 15 tangent theta is this component. So booyah. And then so yep. So this is just what I'm calling A. So I finally figured out that term. Multiplied by sine, that becomes tangent. All right, sweet. But I think that's it. So now everything is as it. And then so this was going to be this, which we just figured out from this equation. And it's going to be the cosine. So this cosine. So we're taking the cosine of that angle. So that's that whole thing. You're taking this, which has that tangent that we just talked about, minus this 700 sine 15 cosine. These cosines cancel here, but this foils in, so we will have a cosine. So now we, so this will just be 700 cosine 15 sine theta minus 700 sine 15 cosine theta. And yeah, so yeah, there you go. So it's just, but yeah, this is brutal. I would get messy with this because there's a lot of different ways to go. But this strategy was just like, well, at the end of the day, I'm just trying to find this, you know, in terms of stuff that I know. And I guess the take-home point for me, so I don't mess up this again, is I'm treating this as something I do not want. But theta, I'm cool with. And everything I know about this triangle, 700 and this angle 15, I'm cool with. You know what I mean? Because the whole idea was taking this, 700 sine theta and 15. So yeah, so I think my take-home point for next time when I do this is, cool, I have a 700, I have a theta, I have a 15. I can use all of them, go for it. And so, and booyah. So then treating theta as like a known value can be very helpful. Even just assuming that theta is a number, call it 30, and just going through that process. Well, I guess you can't call it a number, because if you knew what theta was, you wouldn't be in this predicament. You know what I mean? So yeah, but yeah, it's a variable, but you can set up equations from it, you know, just for sure. And yep, so that's what I did. I did it in reverse. I was like, hey, I want to know this. It would be, and I could, if I knew this, I could know that. If I knew this hypotenuse, I could know that. And to know this, I would have to know this, but I already know that. So how the hell do I know this? Well, I do know this, and I knew that angle. So that was taking it back. So there you go. And then to reiterate, if you know two things about a triangle, a side and an angle, I know everything about this triangle. So I could have, and then I just went the slow way. I said, well, hell yeah, let's get the hypotenuse first, and then go back over here and get this sine component. You know what I mean? So that was a little bit redundant. All right, so hell yes, that was that. And then, you know what I mean, this was the form that we got it in. So we said 700 sine of theta minus 15 is this. It's 700 cosine 15, sine theta. That one cancels. Minus 700 sine 15 cosine theta. Booyah. So I mean, it just is a term. So that's what I have there for that term. That's going to equal 500 sine 90 minus theta. Obviously, we're going to change that to 500 cosine theta. And booyah. So now we just solve. Hey, we just have everything in terms of theta. We can solve for theta. Let's see if we can do so in any cool ways. So what do I do next? I don't even know. I keep that over there. I take this to the other side. So we're going to have... oh, and I see that these two terms are cosine. So I guess that's what I'm getting at. I get this term to the other side and then factor out a cosine. Hell yeah. Oh yeah, because my whole strategy here is just like, well, it'd be sweet to get sine theta divided by cosine theta, which is tangent theta. That's how to collect these sines and cosines. You know what I mean? And I don't have any cosine squareds. I don't have any sine squareds. So I just have sine and cosine floating around in this equation. So that was the take-home. Like, I guess I knew that. I knew that I need to solve for theta. And the best way to do, and I have a sine and a cosine, so why not get something where it's sine theta divided by cosine theta, which is tangent. And it might as well stick with tangent. My calculator doesn't even have a cotangent. I guess these do have catalogs, where you have like catalogs, and then you have like, yeah, is there a cotangent? Because else... yeah, there's got to be. Maybe there's not, though. Yeah, I don't think so. That's bizarre. I don't get how you wouldn't have a cotangent key. Unless I'm just missing something, and it's just like you do, but you just do something. I don't know. Well, obviously, I guess, yeah, duh. Tangent is just 1 over... cotangent of an angle is just 1 over tangent. But still, you can't take the inverse cotangent. But no, I gotta make a video, because I just saying that, it's so dumb. You know what I mean? Like, I should be able to intuit that. But yeah, it's fascinating. I'm sure it's just the ratio flipped, right? Because if I have, if tangent, yeah, I'm gonna go over this. Inverse tangent of the ratio yields the angle. This ratio is where you have a triangle with an angle. And this is going to be your opposite, and this is where the angle is right there, and your adjacent. So the ratio of opposite over adjacent, the inverse tangent of that ratio is this angle. That's associated with that angle. So if I said inverse cotangent, which I do not have on my calculator, yeah, this is wild. Because if I had 1 and 2, like, obviously the angle would be like 35 or something, so I'm going to have inverse tangent of 1 divided by 2. So the cotangent of that, cotangent is just 2 divided by 1. You know what I mean? So if I have inverse cotangent of 2, what do I, as a number, hey, divide it by 1. You know, it's the ratio, so make it a ratio. And this is going to be a triangle with an angle. And cotangent says adjacent over opposite. So it's the, you know, it's saying it in reverse compared to tangent. So the adjacent is 2, the opposite is 1. And these are the same things as saying inverse tangent of 1 divided by 2. So I'm dumb for just not seeing that, but I don't know. I mean, I think it would be better if your calculator had a cotangent button, inverse cotangent, and then you realized that later, because I mean, I'm deep in the game and I did not realize that until just this second. All right, hell yeah. So again, yeah, getting sine over cosine. How do we do that? We have to get the cosine components to one side, which we do, and then factor out a cosine. So hell yeah. So we have, you know, that added over there, factor out the cosine. You know, we have 700 sine 15 plus that 500. And then we have this, which is just one sine component over here, nothing to factor. So what we're going to do, well, even like right here, we could take this to below here, and then this cosine below there. So that's essentially what we do in 2 steps. I take this cosine below the sine, that becomes tangent. I take this below that, and that's that. And so again, this is still, anytime that you have this, anytime that you see a ratio or just even have a number, turn it into a ratio, because the tangent of an angle is a ratio. Like, hey, this is the angle. This is degrees, but the tangent of that is a ratio compared to inverse tangent of a ratio is a angle in degrees. So that's kind of how I write it. And so I'm going to write that one more time. So the tangent of an angle, so this would be tangent of an angle, is a ratio where the inverse tangent of, and I guess I'm just going to say, typically you put an X in there. Man, that's maddening. I like to do just number, inverse tangent, and this is the ratio. So inverse tangent of the ratio gives you the angle, and then the unit. So it's good to, sorry, I munched that. It's good to, I like to do this. This is very helpful, where you get to write it kind of twice. One is just like as symbolic. Tangent of the angle is, and I should have just put number here, you know what I mean? So there you go. So now we have tangent of an angle is a number. Just know to divide that number by 1 because it is a ratio. So and then it spells it out in terms of its units, like tangent of angle in degrees is equal to a ratio. Ratio is unitless, but there you go. Inverse tangent of a number is an angle, gives you that angle. So cool. What's that number? Number divided by 1. It's a ratio. That's kind of the take-home point for this video, or one of them. Inverse tangent of that ratio is the angle in degrees. But yeah, I don't know. Yeah, I appreciate. Yeah, I appreciate people that are okay with this content, because, I mean, this stuff is so heady that, hell yeah, the only way to, like, spoon feed you it is to take bite-sized 5-minute chunks and explain them from, A to B. Sometimes 20-minute, 40-minute tops. But when you're actually using, like when you're just doing one problem and you have to use all this junk, like the entire way, and we're doing this 4 different ways, right? And I spent 2 hours at the coffee shop, and obviously I thought 35 minutes, but hell no, we're doing it our style. I feel, I guess I'm just not 100% comfortable with thinking this is a good method. But I don't know any other way. Because if I get confused, I think I can explain it better, and I do spend time on things. I don't know if I'll reach a perfection or a way that I like, or just get, so saturated with doing it this way that I just want to do it a different way or something. But anyway, so we have the tangent of this angle is equal to that ratio. So what did I was setting up? But this is the stuff that I love, you know what I mean? So hell yeah. So what did we just do? We just said tangent of an angle is a ratio. What this means is that we have a right triangle with this angle that has sides that are equal to this number, divided by 1, this ratio. And because it's already a fraction, it just spells it out for you. That tangent is opposite hypotenuse. So this side's going to be 700 sine 15 plus 500. And this side's going to be 700 cosine 15. If I wanted to know what the hell this side was, well, hell yeah. You know what I mean? And this I did not realize. This is really wild to me because what I did was just solve for the angle. And then once I got the angle, I was just like, well, let's just shove it into the easiest and quickest formula. Like, where did I shove it in? I said tangent of, what did I say? Okay, force. Where did I get this force? Well, I said force was, because it's just right here. It's just these two terms squared, added, and then the square root of them. A squared plus b squared is equal to c squared. C is equal to the square root of a squared plus b squared. So now I'm tripped. I mean, obviously I did the tangent is this ratio. This ratio is just a number. Threw it in my calculator, got the angle. So I guess I took the inverse tangent. Inverse tangent of both sides, which is saying, hey, if I have this ratio, what's the angle going to pop me out? You know what I mean? And that's the angle, 45.2. But yeah, where the hell did I throw this back in? Where do I have an equation with just theta? I'm going to take a pause. Alright, hell yeah. I only took like a 2-second pause because I shouldn't do that. I should just say, well, just, the equation spells it out. So I have 700 cosine 15. Go find that. 700 cosine 15. Oh, okay. Hell yeah. Oh, I see. Yeah, I was just saying, hey, this big right triangle is exactly, 700 cosine 15 divided by, the angle. So yeah, so I have this, that's what I said. I said, hey, if I know this side and the angle, which I just found, then I know the hypotenuse. But it's just fascinating that I didn't spot. Pythagorean's theorem is the last thing that I spot all the time. And that's why I just reiterate that if you're doing anything with trigonometry vectors, write Pythagorean's theorem down as an equation and just make sure you use it just a lot. Because this is how I solve for the force. I knew this side and I knew the angle because I just found the angle. So I said, hey, this side divided by the cosine, and we talked about that. This side is smaller than the hypotenuse, but you divide it by the cosine of an angle, which is a percentage between 0 and 100, or a fraction between, 0 and 1. So it's got to be point something. Hell yeah, it's going to be a smaller number, so you're going to generate a hypotenuse that's bigger. All right, sweet. Cool. Yeah, so that was fascinating. So I could have just got f by taking this squared plus this squared is equal to the hypotenuse. And let's do that, because I think we're not going to get anything with cosine, and that's fine. And we're not going to get anything with the degrees of 105, but we are going to get that initial first answer that force is the square root of this side squared. So that's going to be 700 squared cosine squared 15 plus this squared. So I can do that just in easy steps. I'm going to square the first term, sine squared 15, plus square the second term, 500 squared, plus 2. So I'm going to do this down here. Plus 2, multiply the two terms together. So I'm going to have 500 and then 700 sine 15. And then so all that's the squared. All right, booyah. And so that was the first thing that we did. is we said that force is 500. Oh yeah, and again, we still have that cosine, sine, you know what I mean? So this just becomes 700. So we have 500, 700, and plus that little bit extra. So we get the same numbers. All right, booyah. So that was doing it with the law of sines. Here is just kind of one, you know, how to get there faster going the other way. So I know this 700. I know this one and this one. I just wrote them as 1 and 2. Cool. And then so if I know both of those, what's the next thing that I need or possibly get? Well, if I know this and this angle, hell yeah. That's why I just go right to the hypotenuse. Like, I like to go to the hypotenuse first, then just the tangent, but obviously I could have just come right over here. But so I said if I know this and this angle, I know this. I know this length. Now, it's going to be as a function of theta. That's what I wrote down here. I just know this, check mark 100%, check mark 100%. But yes, to go from here to there, to know this term, it's going to be as a function of theta. If I know the hypotenuse and this angle, I know this is the cosine component, so I know this. That's going to be 4. So I know this length. And I know this length from, so this length is 4, this length is 2, so I know what 5 is, 4 minus 2. So that happens a lot in geometry problems, where you're just like, okay, I know this, and I know this, that means I know that. It's like one of the take-home, there's so many things like that, like a triangle, 180 degrees. If I know two sides, I know the other one. You know what I mean? If I have this, 180 degrees. If I know that angle, then I know this angle. You know what I mean? And so, and this is absolutely wild, comes up a lot, especially in law of cosines, is if I know this length. All right, hell yeah. So if I know this total length, like this length is 15, and then this length is 10, do I know that length? Hell yeah, because I'm going to be 15 minus 10. So you can do it as like 15 minus 10. That is this length is 5. But hell yeah. So that comes up a lot in geometry. So sweet. So know this, know this, know this. If I know this in this angle, I know that. If I know this in this angle, I know that. If I know this and this, then hell yeah. I know this. It's this minus that. So 4 minus 2. And so I have, you know what I mean? And that's going to be 5. So 5 is 4 minus 2. So let's see what I did. So I have 1 is just 700 cosine 15. Cool. 2 is just 700 sine 15. So those are the easy ones. 3 is going to be 700 cosine 15. Sorry, damn it. No, yeah. 3 is going to be this length, 700 cosine 15, divided by cosine of this angle theta. So it's kind of just fun to be able to do that, you know, without writing it down, or, you know, I mean, because if I know this is the right triangle, if I know this side and this angle, this is a smaller component, the hypotenuse is a larger number. So I'm going to take the smaller component and divide it by that fraction. And it's the cosine, so it's this length divided by cosine theta is this hypotenuse. So 3 is going to be this length 1, which is 700 cosine 15 divided by it's this length divided by cosine of that angle. 700 cosine 15 divided by cosine of this angle. That's 3. If I know 3, I know this side. Because this side is just the hypotenuse times the sine of this angle. So that's going to be 4. 4 is 3 sine of theta. And that's obviously redundant, because this is cosine, this is sine. Obviously 3 is just 1 times tangent. It's just this times tangent of that angle. I don't know how to see that or do that without writing it down. So that's why I like to go here. But I could even just go here and there in 2 steps faster than I could write down the relationship between this angle and the opposite over hypotenuse. Even mentally in my head, I could say tangent of this angle is this divided by this. So if I want this, it's already on top. See how that works out? So I can say tangent of this angle is the thing that I want divided by the thing that I already know. So cool, get the thing that I already know over here, and so hell yeah. So the thing that I want is this times tangent of that angle. But that's still, I would still rather go, it's way more intuitive to go to the hypotenuse. Hey, I know a smaller side of a right triangle. What's the hypotenuse? I'm going to divide it by the cosine of that. Just because I can see that this, if this is the angle that I'm going to divide it by, yeah, I think that's easier to see that, hey, this is the cosine component because the sun is shining on the sine component. So this is the cosine component if I'm using this angle. So it's going to be this length divided by the cosine of that angle is this hypotenuse. Cool. All right. And to get from here to there is just, that should be the easiest one. If you have the larger number, the hypotenuse, you're going to just multiply it by a percent to get the smaller number. The percent is what I'm calling sine theta or cosine theta. So in this case, h sine theta. You know, the sun is shining on the sine component. Cool. So that's going to be 4. All right. So 4 is going to be 3 sine theta. Got it. And then 5 is going to be 4 minus 2. Once I got 5, 5 is a hypotenuse of this right triangle, and so I'm just going to go, this component is going to be the hypotenuse times cosine of the angle. Because the sun is shining, this is the sine, this has to be the cosine component. Cool. I knew that this was this angle because I think what would be the fastest way to do that? I know that this angle, sometimes it's really good to come up here and kind of do this Zorro shape, parallel lines. You know, this is just the horizontal, you know, kind of, I mean, if this is the x direction, this is just parallel to the x direction, so parallel to horizontal. But how do we get this angle again? You know what I mean? That is fascinating. Right here, I think. Well, sure. If this is 15, this is 75. So this angle is going to be 105. And then if I know this angle, damn it, how still do I don't know how to get it yet. Oh, that's a good question. Oh, yeah, it's just from here. Yeah, this, yeah, even simpler. This triangle, this was my, this was theta. Even though it's a variable, you know, it's the variable that we're trying to convert things to. So cool, if this is theta, this is the right triangle. By complementary angles, or just knowing that, hey, this is 90, 180 minus 90 minus theta is this. So let's spell that out. 180 minus 90 minus theta is this angle. And what is that? That's going to be 90 minus theta. And so, but it's just really easy to see, you know, this is where, like I would rather do this every single time. I don't know why I like to do things like this. I mean, obviously, if you're in a test or you just want to get on with life, but until you have the proofs just drilled into your head, there's no reason to do the trick. Just to be like, oh, these are complementary. Meaning that if this is 180 degrees and it's a right triangle, this is always going to be 90. So the difference, these added have to add up to 90. So if this is theta, theta plus something is equal to 90. Theta plus something is equal to 90. Therefore, it's always the case that this is 90 minus theta. You know what I mean? And then this is 90 minus theta. Yeah, but even that, I mean, even just that's, I don't know, I can't do that without trickery, you know what I mean? But I for sure know that, hell yeah, just by memory, that if I have this angle, this is 90 minus that. Based on this equation or this equation. 2 ways to get it. 180 degrees, you know, back to 8th grade, middle school. Or just knowing this is always 90 for a right triangle. and then it's just these two angles have to equal 90. This little equation generates that 90 minus theta. So then, if this is another right triangle, you can just do it again. 90 minus theta, well, this has to be, and I still can't see that. If this is 90 minus theta, I'll have to, but yeah, because this might be 90 plus theta. And I guess it couldn't be, because this couldn't be, okay, cool. If this is a right triangle, this could never be 90 plus theta. So that's cool. So yeah, so if I see this 90 minus theta, this is just always theta. But I seriously would have to, let's do the 180. We have 180 minus 90 minus 90 minus theta. All in parentheses. This is 180 minus 90 minus 90 plus theta. So that's going to be 0 plus theta. This is theta. Brutal. But yeah, always good to do. Alright, so I think that leaves us with, we know this hypotenuse, and we know that this side is the hypotenuse cosine of that angle, angles theta. The hardest part about taking, sine of an angle minus 15, so we had, theta minus 15 is this angle. This was the angle that if we knew, we could relate this hypotenuse to this sine component. But we had to get it in terms of other things. Our calculator could do this, but still our calculator has to do all the same things that we just did. So there is that. It has to program that in. And that's kind of wild. There's no way around it. I'm sure there's technically ways around it. Calculators never do exactly what like this. They always probably try to find as many tricks as possible to generate the same number in the fewest amount of steps. All right, so but yeah, that was that's the hardest part of taking something like this and getting the components that you actually want is well, just drawing the separate triangles, you know what I mean, even that. But yeah, it was fascinating because it even spelled it out. This problem spelled it out for me because typically sometimes you don't have that option. Like all you have is I don't know. Like let's say you had this as your hypotenuse and you had to add these angles and it was 15 plus theta and you didn't know what that was. So, you know what I mean? Let's say this angle was theta and this was 15, and then you had to take this, just this sine component. Alright, hell yeah. So I just set up a little scenario where we have 700, a hypotenuse, we have theta, and this is 15. And man, this is really difficult. So that's all I have, is just like, I have 700, and I just know that here's my angle, theta plus 15, and I want to take 700 sine theta plus 15. You know what I mean? So all that would be is like, hey, here's my hypotenuse, and if this is the angle, this means this is the right triangle, and then this is this component. But man, this is brutal. So I guess but this is good because the strategy is like you can use anything, any numbers in terms of theta alone and 15 alone. So right here I can see that here is a hypotenuse, and if this is the angle theta, not theta plus theta, this was the hypotenuse of theta, theta plus 15, this triangle. But if I just have hypotenuse of theta, then I come in here and drop down a right triangle. So booyah. So I at least saw that part. And now, I mean, I can just start spelling it out where I can say, hey, this is going to be 700 sine theta. Cool. This is going to be, I don't know that, but I do know what this is. So I'm going to say, hey, this is 1. This is 2. This whole length right here is 2. And that's going to be 700 cosine theta. And so now what do I need? And then we can, you know, if this is theta, I'm sure. So let's do that whole trick of like, hey, let's start drawing lines like this. This is going to be theta plus 15. This angle never gives you much of anything good. But if I know this is 15, same thing. This is 75. Oh, so now we're going places. This is 105. Oh, sweet. So if I know this is 105, guess what? Look at this. This is 75. And the couple strategies here are like parallel lines make this Zorro. I always look for that. You know what I mean? That's the take-home Zorro. But then, man, I even missed this one where you just have the angles like this. If this is 75, this is 75. Sweet. And so guess what? I know an angle and a side of this triangle. I know everything about this triangle now. And so, and I don't even, and check this out, I don't even have to say this is 75. This is just 90 minus 15. So now everything's in terms of 15 and theta. And so this is 90 minus 15. So now we're kind of writing it from the more technical perspective. So if this is 90 minus 15, this is going to be, what is this? Well, I mean, just from the looks of it, this looks like 90 plus 15. But why is that? So I have 180 is equal to 90 minus 15 plus something. You know what I mean? So it's going to be 180 minus 90, which is 90, plus 15, 105. So sweet. So what would that be? That's going to be 90 plus 15. So 90 plus 15 is this angle right there. That's going to be 90 plus 15. So hell yeah. Oh, we're going to run out of juice. This is a really good place to, you know, end it kind of and work through this one. All right, sweet. So yeah, so that's the angle in terms of 15 and theta. Oh, yeah, if this is 90 minus 15, cool. I remember that now. This is just 15. And now I don't have to take, you know, I don't have to use this because I already, what did I find? Sorry, I found this length is 1. And because I found this length, it's not a hypotenuse, it's a side, but I can know this angle. And this angle is 15. So I can stay away from any, you know, so again, so yeah, you don't want that, you don't want to what we started with is sine theta plus 15. We don't want to compound the issue, even though it would be fine. It would be actually, I don't know what I was saying, but it would be fine to use different values. You should do that. You should take a trigonometry problem and use this. Use 75, you know what I mean, instead of the 15. And it's the same thing that we did originally, where we get kind of what looks like the law of cosines, but it has a sine and not a cosine. Well, it's just because we used, you know, different terms that basically mean the same thing. And I think that's, I mean, this is just basic trigonometry, how like, hey, all the right triangles have, you know, two components that are related to the hypotenuse, and guess what? All three are related. That's it. All right. So we have this side. It would be, what would be cool to, what do we actually need? We need to find this whole thing. But I know this side of this right triangle, so I can find the hypotenuse. I'm going to call that 3. So I'm going to say 3 is one of the sides, 1, divided by cosine 15. That trick, you know, I mean, divided by a smaller number is the hypotenuse. Okay, sweet. And do I know this? No, so I need to find this length. It would be sweet if I could. And hell yeah, I know that length. This length right here is, this full length right here, I'm going to call it 4. So 4 is 700 cosine theta. So 4 is 700 cosine theta. Cool, so I know this full length. What I really want is this length, and that's going to be 5. So sorry to overlap 4 and 5. 4 is this full length, 5 is this length. So 5 is 4 minus this little chunk. And that little chunk, I guess we're going to call it 6. So 6 is, and where do you want to go? Do you want to, If I did this, I would have to relate it to the tangent, so let's not do that. Let's just say, hey, that's going to be 3 sine of 15. The hypotenuse, sine, so 3 sine of 15. Hell yeah. So that's going to be 6. And 5, this length right here, which I'm needing to get this length, right? This is the hypotenuse, so 5 is the total length 4 minus 6. Cool. Once I know 5, then I can know 7 right there. So 7 is 5, and then it's the sine 15. So hypotenuse sine 15. So sine 15 is 7. Now this full length is what I was after. That's where you can just get into the weeds of just like, what the hell were we even trying to find? Well, we were taking 700 sine of theta plus 15 was this. And so that's going to be 3 plus 7. So sweet. So sine is 3 plus 7. And I got a minute, I think. All right, more time on the clock. So we have, so hell yeah. So we have 700 sine theta plus 15 is 3 plus 7. And 3, I guess let's do the 3 component first. 3 is 1 divided by cosine 15. 1 is sine. Yeah, so here we go. So it's going to be 700 sine theta divided by cosine 15. That's that. Hell yeah. And then we're going to add it to... I feel like I made a mistake because usually when you do this, you don't get, something on top and bottom, but whatever. I can double check it. So 7 is going to... plus 7 is going to be sine 15 of 5. Oh, yeah, this term's going to be enormous. So I'm going to come down here. So we have... so 5 is 4 minus 6. 4 is, where the hell is 4? Yeah, 4 is 700 cosine theta. So we're going to have 700 cosine theta minus 6. 6 is 3 sine 15, which is 3 again, which is this. So we have 700 sine theta cosine 15. But sine 15. So that was bummer. So 5 is 4. So I got 4. 4 minus 6. 6 is 3 sine 15. So I got 6. Done with 6. And that's 5. But yeah, 7 is 5 sine 15. So hell yeah. So we got 5, and then it's sine 15. Brutal. And now we're going to make it look all shiny. Let's see. Oh. Alright, hell yeah. So we're back, and I just looked up, this is such a good book. It's Eschbach, Handbook of Engineering Fundamentals. So what we have is sine theta plus 15. It's got to look like this, and I just threw in, you know what I mean? So we got to here, and it does not look like this. So we are going to, let's just redo it. Instead of using numbers, I thought that was a good way. And I'm gonna try to, on my off time, go back and just use numbers. But for this, I think what we'll try to do is just redo it and try to do it just a little bit crispier. Okay, so this one's going to be 15. Hell yeah. This is going to be 75. This is going to be, this is going to be a 90. This is going to be a 90. This is 75. This is 75. This is 15. Sweet. This is going to be theta. Cool. And so this right here is going to be 90 minus theta. But we can always just use this term right. Oh, bummer. No. Never mind. What we're trying to do is this is going to be theta plus 15. So we're trying to figure out what this height is. So we have 700 right here. So hell yes. Now we just go for it. This is going to be 700. Bummer. 700 sine of theta. I just need this. That's all I need. So cool. This is going to be 700 sine of theta divided by... this is where I messed up. Cool. This is the angle right here. But this component is a cosine component. It's an adjacent component. So I bet you I messed up right there. So this is going to be 700 sine theta divided by cosine 15. So let's see if I messed up right there. So 3 should be 700 sine theta divided by cosine 15. Nope, didn't mess up right there. So we're good to go right there. All right, so now how do we actually find this? Well, we're going to take this whole thing. Well, we don't know that. So we're going to take this. I do know what this is. This whole thing right here is going to be 700 cosine theta. Hell yeah. And yep. Yeah, so I had 4. How did I get this 6? Oh yeah, no duh. Okay, yeah. So so now I know this full length and I know this component because I know all sorts of things about this. So hell yeah. So this component right here, we'll just take the hypotenuse, 700 sine theta divided by cosine 15. And then we're just going to go times sine 15. So hell yeah, because that's the sine component, sine 15. Alright, sweet. Which is the same thing as 700 sine theta tangent 15, which we could have had right here. If I have the adjacent, this times tangent 15 is the opposite. Because tangent 15 is opposite over adjacent, and opposite is what I want to know. Sometimes I do that over the thing that I do know, 700 sine theta. And so, hell yeah, this times tangent 15 is the opposite. That one's harder for me to remember, though. I have to write this down all the time. All right, we're getting close. So we have this component, we have this total length, and so then I can get this length right there. That's going to be this total length, 700 cosine theta minus 700 sine theta divided by cosine 15 sine 15. Now this is just tangent. I'm just going to leave it like that. Alright, so that is that length. No, it's this length. This minus this is this length, this hypotenuse. And so then I can find this component. That's all I'm really trying to do. Like, hey, I have this component, I already know it. And I need to add it to this component. So that's going to be this component sine 15. So now I have sine 15. Damn it, I think I have the same thing. I don't know. Maybe I actually just typed it in wrong. Maybe this is totally right. So we have sine 700 sine theta cosine 15, and then plus all of that to get that. Yeah, let's type it in. So theta is 25, x is 15. So let's do it. So we would have, and then, this would be 700 times this. So we're going to have 700 sine theta cosine x 15, right? Plus cosine theta sine x is 15. And then did I multiply that by 700? Hell yeah. Cool. Oh, yeah, no. I was right. I actually, typing this in, I typed it in wrong. So, cool. So that's alpha A. Whoops. Bummer. Yeah, that's alpha A in my calc. Oh, no. I need to store as alpha A. Cool. So then if we type in all this jazz, brutal. This plus this, right? Which is just this. We did it right the first time. But it was good to go over it again because brutal, and I don't think doing numbers was the... Well, I mean, we got here with numbers, but we got here... It just gets messy, like, writing all this stuff in. So that's where numbers are kind of useful. All right, let's write it in. So we have 700 sine theta divided by cosine x plus parentheses 700 cosine theta minus 700 sine theta divided by cosine x. I don't need to write x, I can do 15, but whatever. Times sine 15. And in your calculator, if you do this divided by this, you can just instantly multiply by the next term. It doesn't put it downstairs. You know what I mean? So it's kind of fascinating. Just how calculators work. My brother was saying if they didn't do that, that would be trouble. You know what I mean? Because I was just like, yeah, it seems like they would just keep dividing whatever's, but no. If you do this divided by that, the next term you multiply is always upstairs. And my brother was like, hey, yeah, if they didn't do that, all hell would break loose. They have to do it that way. You know what I mean? So, yeah. I mean, you just need some sort of standard. All right, sweet. Oh, I'm just going to... That's it. All right, booyah. We get the same term. So, hell yeah. So, somehow that simplifies to that. I'm going to pause the camera. I can't see it. Because what I see is a sine squared 15. Oh. Check this out, though. No duh. So cool. I have a triangle. It's 15 degrees. This in its unit of 1. This is sine 15. This is cosine 15. And right here I'm going to have a sine 15 squared term. Well, let's see. Let's say I do. If because what do I know about sine 15 squared plus cosine 15 squared is equal to 1. So cool. So sine 15 squared is 1 minus cosine squared 15. So yeah, I got tripped up. I mean, that's the whole idea of doing these videos, to do enough trigonometry where, yeah, you can just kind of see the pattern. So this is going to be negative 700 sine theta cosine 15 times sine 15 squared, which is going to be 1 minus cosine squared 15. So this is just going to be 700 sine theta cosine 15 plus 700 sine theta cosine this squared, but I got 1 down there, so I'm just going to put it up top, cosine 15. Hell yeah. So that's how that simplified. And then we're going to have I got to FOIL these terms, so I'm going to have 700 cosine theta sine 15, and then I have to add that term, which is 700 sine theta cosine 15 minus 700 sine theta, so those terms cancel. And hell yeah, so I'm just left with that, which is 700, and that's how it's supposed to be, 700 cosine theta sine 15 sine theta cosine 15. And, I mean, you can write it, how many ways can you write that? But anyway, so we have 700 cosine theta sine 15 plus 700 sine theta cosine 15, which is the same thing as writing it, just opposite, sine theta cosine 15 plus cosine theta sine 15. Which, yeah, now I'm seeing the other ways to write it, which is the same thing as writing it as cosine 15 sine theta plus sine 15 cosine theta. So that's these two are just kind of flipping those two terms. And then so we would have sine 15 cosine theta plus cosine 15 sine theta. But this is stuff that I need to do mentally, because especially if there's like 3 different paths, and trigonometry is that way. There's 3 different paths to get places. You have a right triangle with 3 things related. You know what I mean? So it's just kind of fascinating. Yeah. But yep. I mean, the take-home point is if you have sine of an addition of the angles, you're going to have a sine and a cosine component in one term. In each term, you're going to have a sine and a cosine component. Where is if you take the cosine, you're going to have a cosine, 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 cosine. So, and the nice thing about it is if this is plus, this is plus. If this is minus, this is minus. So yeah, so it's a pretty easy one to memorize, but man, you would be able to mess it up. But yeah, I guess. And what would be a way? Let's say you thought you did a pretty good job of memorizing this. Where yeah, the cosine of theta plus 15 is going to be sine, sine, cosine, cosine. You know what I mean? Theta 15, theta 15. And plus. If it's negative, it's going to be negative. But yeah, one way that you could do this is just set up a little triangle. You know what I mean? Do 15 degrees and this 25. Either add them or subtract them. You know what I mean? Add them together and then try to find the sine component. That's what we did. And then if you memorize this, see if your memorization matches reality if you throw in any value here. And obviously just throw in 1. This would be the classic, hey, just make this a unit triangle where the hypotenuse is 1. So then you just have 1 multiplied by this. Alright, I enjoyed this video. I think it was good. And I think we covered all the pages that I wanted to cover. So yeah, that was pretty sweet. Heck yeah. Yeah, and I think we already covered law of cosines. And so many people do anyway. Yep. And we could easily cover that in a different video. So this was a sweet one to end on, you know what I mean? Where you have, what are they? I don't know even what you call it. It says functions of the sum and difference of 2 angles. Yeah, so you have the sum of 2 angles, or the difference of 2 angles, and the functions. The functions are the sine, cosine, how that's related to a larger right triangle. So I'm saying, hey, I'm adding those 2 angles together. They're part of this larger right triangle. They're functions of this larger right triangle. This being the sine, this being the cosine. Cool. And if we were trying to find the cosine of these added, it would be cosine, cosine plus sine, sine. If you know what I mean. And so we were trying to find the sine component, so it's going to be sine, cosine plus sine, cosine. You know what I mean. And you can flip-flop those. That's the interesting thing. Alright, hell yeah. Alright, sweet. Thanks for joining me on this one. And for sure. Alright, hell yeah.